Identifications of potential outliers is important in many application domains such as network intrusion and financial fraud. We use several strategies to measure how much the data point can contribute to the overall outlying score of a scatter plot over time with the following main three design considerations. In the case of international debt in 2017, it would be relatively easy to spot out India and China as outliers in 2D projection as well as projecting it to the population's dimensions, or Pakistan to only debt dimensions. However, in the examples of life expectancies, Iraq, El Salvador, and Iran falls into the center of any marginal distributions, but they are evidently outliers in pairwise projections. Design decision 2. Binning. To handle a large number of data points, we will use leader binning. The idea is similar to site cover. It starts at the data point and group neighboring points within a proximal radius. From then, we will build the minimum spanning tree on the set of leaders, which is significantly smaller than the raw data points. Design decision 3. We use box plot rule on MST lengths to calculate the outlying score to find out which data points are outlying and which points are not outlying. After computing outlying on the original scatter plot, we keep bounds of the box plot rules. This makes our approach robust to outlying computations on other leave one out plots. Moreover, before computing outlying on leave one out plots, we check if the remote point is in a singleton cluster or not. If yes, we perform an outlying computation. Otherwise, we skip this calculation to minimize the computation time significantly. We consider a point is outlying. If we leave it out, it will decrease the outlying score. Say if we leave Iran out, then we'll have another outlying score reduced comparing to the original outlying score. So this Iran is considered as outlier. Besides the outlying point, we also consider the inliers. Let's say South Sudan in this case, which are defined as observation that lies in the interior of a statistical distribution, and their absence allows identifying outliers easier or possible. And if we remove South Sudan, we'll see that the outlying score will increase. We can see now the two countries like Timor-Leste and Cambodia will become outliers. In this case, we define this point as inliers. Our approach is that for a scatter plot, at each time point we're going to compute the outlying score using the box plot rules. We repeatedly leave a data point out of the plot and recompute the outlying score. At the end of the computations, for each data point we obtain a temporal signature of its contribution to the outlying score of two variables in consideration, as shown in the stream graphs, where the green is for positive contributions or masking effect and purple is negative contribution or swamping effect. Now we demonstrate outliagnostics on two real-world datasets. Use case number 1 is the US employment rate. We can quickly spot out that in this time period, Florida is an extreme outlier. After investigating, we find out the reason is due to the Irma hurricane in September 2017 that affecting the employment rate in Florida. Similarly, if we look at Louisiana, we can see that at this time period, it was extremely outlying. After investigating, we found out that at this time period, Louisiana was affected by the Katrina hurricanes. Use case number 2. In this use case, we use outliagnostics to monitor health status at a high-performance computing center at a university. The two variables are CPU temperatures and pen speed. This shows the events at 12 p.m. On Wednesday, September 26, 2018, the CPUs on Compute 313 suddenly became overheated. Our outliagnostics was able to pick up the events and alert the system administrator to make CPU replacement the malfunctional CPU before it harms other neighboring CPUs. As shown in this scatter plot, fan speed on compute 312, 311 have pumped the rate as they sense the heat. We discussed our approach and highlighted this event through an informal interview with Dell experts and HPC director. They valued diagnostics from our prototype and suggested thermal experts in their team to the interesting correlation between CPU temperatures and fan speed. Outliagnostics are currently deploying additional dimensions such as real-time memory usage, power consumption, and CPU load. I/O and bandwidth are among the other future iterations in these ongoing collaborations. Now we show the computation times of our approach. First, as shown in this chart, one algorithm takes the most time to bin since the data distributions in this scatter plot is sparse and hence it takes a lot of time to find the right coverage to guarantee at least 50 liters. In contrast, US unemployment rates and the world unemployment rates are well spread and take less time to bin. Notice that the same binning is reused for all leaf 1 hour plots. This chart shows the computation time of original scatter plot, which is averaged over the entire time series. As depicted, the computing minimum spanning tree in green is the most expensive step, while applying the box plot in red is fast. This last figure shows the average computation time for each leaf 1 hour subplots. As the number of data points in scatterplot increase from left to right, the total computation time decreases. This is because the outlying computation time is independent of n. More importantly, our algorithms checks if the left out data point is in singleton cluster or not. If yes, we perform the computation. Otherwise, we skip, since removing a data point from crowded bin will not affect the final outlying score. This strategy allows our proposed approach to scale well with the larger datasets. Other use cases can be found on our project page, and thank you for watching.